Thank you. All right. Well, firstly, let me say thank you. I'm really happy and deeply honoured to contribute to this wonderful event commemorating such an inspiring and great mathematician. So the subject I'm going to talk about is joint work with Ivan Smith, as was mentioned, and it is about a relationship between two kinds of invariants. One is algebraic K-theory of algebraic varieties, and the other is Lagrangian cobordism groups of symplectic manifolds. So that's these related by mirror symmetry. So that's understanding this relationship is a project that Ivan and I have been working on and building up a dictionary. It's very much, I mean, we don't have any real final destinations. We're just working on building up the dictionary, and so it's the kind of subject that would be wonderful to have contributions from anyone, and would have been wonderful to have had more opportunity to talk about it with Atiyah himself, throwing out ideas at us. So in fact, I should confess that rather than dealing directly with algebraic K-theory, we study it via the Chern character to the Chow group, which is a rational isomorphism. So most of, well, the whole talk will really be about comparing cobordism groups with Chow groups, but I couldn't resist putting algebraic K-theory in the title, because on the one occasion I did have the opportunity to meet Atiyah. He asked me what I was working on, and I started telling him about this project and started explaining what Lagrangian cobordism groups were, and he said, there must be some K-theory in the background. And so, I mean, which is exactly correct. So I couldn't resist putting that title. All right. So that's going to be the focus of the talk. So let me situate that this aspect of mirror symmetry is not as familiar as some others. So let me situate you. Oops. This screen. There we go. So let me situate you with respect to more well-known versions of mirror symmetry. So for our purpose, mirror symmetry will be a relationship between smooth algebraic varieties Y and symplectic manifolds X. It says that there exist many pairs Y and X like this, called mirror pairs, and we have countless constructions of putative mirror pairs, such that the algebraic geometry of Y is reflected somehow in symplectic geometry of X. So one of the most famous of these relationships is Kontsevic's homological mirror symmetry conjecture, which predicts that the derived category of coherent sheaves on Y should be equivalent to the derived Fukaya category of X. So these are triangulated categories. I'm barely going to mention them for the rest of the talk, because what we're going to do to this equivalence of triangulated categories is consider the associated isomorphism or conjectural isomorphism of growth and deep groups. So growth and deep group of the derived category of Y should be isomorphic, just isomorphism of the abelian groups, of the growth and deep group of the derived Fukaya category of X. Growth and deep group being free abelian group on objects, modulo relations coming from the distinguished triangles, triangulated structure. Now, essentially, almost by construction, the growth and deep group of the derived category is isomorphic to the algebraic K-theory of Y, which, as I mentioned, we're going to study via its Chern character to the Chow group of algebraic cycles. The Chern character has some denominators, so we need to tensor with Q, and then when we tensor everything with Q, this becomes an isomorphism. So it's a rational isomorphism. Just put all those Q's in there. Nothing we've got to so far involves understanding torsion in this isomorphism. So we're not, at this stage, we're not losing anything. Okay, so this algebraic geometry invariant we're going to study is the rational algebraic K-theory or rational Chow group. The symplectic side, well, there's this invariant of a symplectic manifold called a Lagrangian cobordism group, which I will tell you the definition of a bit later. And this admits, by work of Duran and Cornea, admits a surjective homomorphism to the growth and deep group of the Fukaya category. So this is some, and it's a very important and interesting question whether this map defined by Duran and Cornea might be an isomorphism or not. A sort of question about how many of the relations in this K group of the Fukaya category, a sort of algebraically cooked up thing, come from this geometric Lagrangian cobordism group. So the idea of my talk is to try to compare these two invariants, one from the world of algebraic geometry, the Chow group, and one from symplectic topology, the Lagrangian cobordism group. So my plan for the talk, so of course the Chow group is a far more developed subject, and much more is known. And our idea is to try to understand if we can, how much we can translate into the world of symplectic topology via mirror symmetry of what is known. And I should confess that our original plan was to leverage cases of homological mirror symmetry which are understood to establish new results about the Lagrangian cobordism group via this diagram. And then, well, for the ones we were maybe most happy about, I explained them to Denis Aru, who explained how to get them in a much more elementary way. So the upshot was that we, rather than having a really interesting result that crosses via deep, complicated mathematics, we have a dictionary between known results about Chow groups and sort of geometric symplectic arguments about these Lagrangian cobordism groups. All right, so the plan for the rest of the talk is for me to explain explain some basic structural results and computations of these Chow groups, and then once I've done that, I'm going to pass to these Lagrangian cobordism groups and explain what those results about Chow groups correspond to in the symplectic world. All right. by the way, I should have mentioned, I was meaning to write here that, in fact, this mirror symmetry, as I'm going to talk about it, works best for Calabi-Yau varieties, which is sort of like a zero curvature condition. Okay, so we'll only consider those examples. All right, so here's the definition of the Chow group, an algebraic variety. It's the algebraic cycles modulo rational equivalence. And the first important piece of structure that we have to consider is the cycle class map, which just takes an algebraic cycle in Y, maps it to its fundamental class in the homology of Y, which of course is going to be a Hodge class. It's going to be a PP class. And the integral Hodge conjecture, the original version said this map should be an isomorphism. First counterexample was constructed by Atiyah and Hirzebruch, and the corrected Hodge conjecture is, or what we currently refer to as the Hodge conjecture is that the cycle class map tensored with Q is an isomorphism. Okay, so I'm going to give numbers to the various bits of information or structure or computations in Chow groups that I'll talk about, and then I'll run through the numbers one by one and explain what they correspond to in the world of Lagrangian cobordism. Okay, so that's number one, is the cycle class map and versions of the Hodge conjecture. All right. Number two, the Abel-Jacobi map. So we take the homologically trivial algebraic cycles, the kernel of the cycle class map, and the Abel-Jacobi map maps those to the intermediate Jacobian. And roughly speaking, its definition is you take a homologically trivial algebraic cycle, take a topological null homology for it, C, or a bounding topological chain, and then integrate over C. Integration over C defines the Abel-Jacobi map applied to that homologically trivial cycle. And the intermediate Jacobian is designed to receive this definition. All right, so that's the next important bit of structure that we're going to consider. All right, number three is the first computation that we'll translate. So I mentioned that the version of mirror symmetry that we're interested in works best for Calabi-Yau varieties, which is a zero curvature type condition. So the only curves, the only one-dimensional smooth algebraic projective varieties are elliptic curves. And here, the cycle class map maps to the even dimensional homology of Y, which of course is just H0 and H2, so that's Z squared. A choice of base point in Y defines a splitting. And the kernel of the cycle class map is the zero homologically trivial zero cycles, which the Abel-Jacobi map maps isomorphically to the Jacobian, which is isomorphic to Y. So we have a split short exact sequence. So we have a direct sum of this discrete bit Z squared with this continuous bit that's just isomorphic to the elliptic curve Y. That's our abelian group. Right, so that was a one-dimensional example. Now we pass to two-dimensional Calabi-Yau varieties. So so some very nice two-dimensional Calabi-Yau varieties are K3 surfaces. And sorry, the whole talk, things are sort of not presented in chronological order, but the first result about Chow groups of K3 surfaces I'm going to mention is due to Beauville and Voisin, who explained that there's a natural splitting of this short exact sequence. So the cycle class map is surjective onto the Néron-Severi group, which just consists of H0 and H4, two copies of Z, together with the Picard group. It's the part in H2. And this Beauville-Voisin result says that there's a natural splitting of this cycle class map, so that the Chow group is isomorphic to the homologically trivial zero cycles direct sum with it's what's called the Beauville-Voisin subring. So really what it means, since the cycle class map is actually an isomorphism on H2 in degrees 2 and 4, really what it's saying is there's a very special class in the zero of zero cycles, very special kind of point on a K3 surface. And one way of describing this very special class is that any point lying on a rational curve in your K3 surface has its corresponding class in Chow naught, it lies in this Beauville-Voisin ring. Okay, so that's sort of the discrete part of the Chow group of our K3 surface. And then about the continuous part, well, there are many. Well, one of the key results about it was proved by Mumford in '68, and says that in fact this continuous part, this group of homologically trivial zero cycles, is really massive and hard to get a handle on. It's infinite dimensional, which means that if you take the natural way of parameterizing homologically trivial zero cycles, which is the map from Y to the 2D into this Chow homologically trivial zero cycles, just sending a tuple of points to the corresponding difference of classes in the Chow group. This is not surjective for any D. So really it says you can't parameterize this Chow group, this homologically trivial Chow group, by any finite dimensional algebraic variety. Okay. So that might be seen as a bit of a surprise that there's these zero cycles are really huge and hard to get a handle on. However, part of the Bloch-Beilinson conjectures says that if your K3 is defined over a number field and you look at the homologically trivial zero cycles generated by points defined over that number field, and that bit is actually torsion. So it's very, very small. So that's in stark contrast to Mumford's result. Okay, and now the final results about Chow groups I'm going to talk about. This is certainly not in order of difficulty, but these are the things that we managed to translate into this symplectic world. One is a pretty straightforward lemma. It says that if you've got if Y contains no curve, which can only happen if Y is an analytic space, then chow naught of y has no relations at all. It's just isomorphic to z to the y. It's generated by the points of y. But in contrast, if y is instead algebraic over an algebraically closed field, then the group of homologically trivial zero cycles, chow group of homologically trivial zero cycles, is divisible. So recall that divisible means you can divide. So for any element in any integer k, there exists another element such that when you multiply it by k, you get the original one. So you can sort of divide by integers. So this is saying that there are many, many relations. And the way you prove this result, or the way that Bloch proves this result, is by, say it suffices to prove that any class P minus Q is divisible, the points P and Q on Y. You find a curve passing through P and Q. Its Jacobian is a torus and therefore is divisible. So P minus Q admits you can divide P minus Q by any integer just by looking at points on that curve passing through P and Q. But you need it to be algebraic to be able to get this curve passing through P and Q. For analytic spaces, there might just not be any curves at all. Okay, so that is the end of the sort of overview of results about chow groups from the world of algebraic geometry. And now it's time to pass to the world of symplectic geometry and see what these results and structures correspond to. So let me introduce this invariant from the world of symplectic geometry, the Lagrangian cobordism group. So it's associated to a symplectic manifold X, and it's by definition the free abelian group on Lagrangian submanifolds of X, modulo relations generated by Lagrangian cobordisms. So a Lagrangian cobordism is a Lagrangian submanifold of X cross C, such that outside a compact set, it's just given by a union of rays in C, these rays, theta I constant, Cartesian product with certain Lagrangians Li, so Lagrangians in X. And when you have such a Lagrangian cobordism, it defines a relation in your Lagrangian cobordism group, which is just given by the sum of these Lagrangians Li at the ends of the cobordism. So this was first considered by Arnold, 1980. And I mean, the idea is that one of the fundamental questions in symplectic topology is to try to classify Lagrangian submanifolds up to some sort of equivalence relation. A natural equivalence relation would be Hamiltonian isotopy, but that's typically far too difficult a problem to try to solve. There are very few symplectic manifolds where that classification problem is remotely tractable. And so this Lagrangian cobordism relation is a coarser equivalence relation where we might have a hope of classifying Lagrangians up to this notion of equivalence. So it's very natural from the point in symplectic topology. All right, so now let's get to work translating. The first bit of structure to consider was the cycle class map, taking an algebraic cycle to its fundamental class. And it's not hard to guess what the analog of that is. Well, we need to take the oriented cobordism group, which means we take oriented Lagrangians. And oriented cobordisms. So that the fundamental cycle of our Lagrangian defines a class in homology. But then if we take that, if we orient everything, then we get a homomorphism from the oriented cobordism group to the homology of X, sending a Lagrangian to its fundamental cycle. So if you drew a picture of the Hodge diamond here, this is always going to be a class in middle dimensional homology, so it's always going to lie on this sort of horizontal line in the Hodge diamond. Whereas if you had drawn a picture of the cycle class map, that always would have mapped to this vertical line. This is the mirror in mirror symmetry, the 45-degree reflection in a 45-degree line that interchanges these two. Okay, so that's the analog of the cycle class map. And the analog of the Hodge conjecture is the question about what is the image of this map, i.e. which homology classes can be represented by Lagrangian submanifolds. Which is a central question in symplectic topology, and have nothing in particular to report about answering this question using this chain of ideas. But I will note that recently Benoit and Autumn constructed counterexamples to the integral Hodge conjecture for Calabi-Yau, well, Calabi-Yau in our sense, varieties. So we now have some, those would be interesting candidates to look at the mirror of, to study. Might be a clue for an interesting direction to look at this, this question of representability of Lagrangian homology classes. Okay, so that's translating the cycle class map and Hodge conjecture. I'm going to jump ahead to number 3, which was the example of the elliptic curve, whose Chow group was isomorphic to the Jacobian, which is another copy of Y, direct sum Z squared. The isomorphism given by the Abel-Jacobi map together with the cycle class map. And the mirror to an elliptic curve is a 2 torus equipped with a symplectic form. The cycle class map, as we just saw, is the map taking a Lagrangian to its homology class in H1, which is also isomorphic to Z squared, analogously to, that corresponds to the Z squared, which is H0 plus H2 of the elliptic curve. And the question is, what is mirror to the Abel-Jacobi map in this symplectic world? So in this case, this actually has a very simple answer in terms of very straightforward basic symplectic topology. And the key to it is to observe that if you have a Lagrangian cobordism V and a class in H2 relative to the boundary, then the symplectic area of the projection of that class to X, a symplectic manifold, is 0. And this allows us to define a well-defined map from our oriented cobordism group of the 2 torus, homologically trivial group, to R mod the subgroup generated by the area of the 2 torus, total symplectic area of the 2 torus. And this map takes a homologically trivial combination of Lagrangians, chooses a topological cycle, well, a smooth cobordism between them in X, and the map sends it to the symplectic area of V. And this is clearly well-defined up modulo integer multiples of the total area of the 2 torus. So I'm going to call this little aj. So it's not quite what we wanted, because the algebraic geometry, in algebraic geometry world, the Abel-Jacobi map mapped to the Jacobian, which was a 2 torus. For this map, we've constructed maps to S1, or 1 torus. But this is in fact mirror to the composition of the Abel-Jacobi map with a projection of this elliptic curve to S1, which is the so-called Strominger-Yau-Zaslow fibration. So if you want to get an isomorphism with the what we saw in the world of algebraic geometry, you actually need to consider not just the Lagrangians, but what's called a Lagrangian brane, which is a Lagrangian equipped with a unitary local system. So when you decorate your Lagrangians with that extra bit of structure, then a result of how shows that you get this, the desired isomorphism between this decorated Lagrangian cobordism group and the Chow group of Y. And this inclusion of the unitary local system is very makes perfect sense from the point of view of mirror symmetry. These are the natural objects of the Fukaya category are Lagrangian branes in this sense. Okay, now very briefly, you might want to actually prove this result for yourself. The key step is to show that this map little aj is an isomorphism, and that uses 2 basic constructions of Lagrangian cobordisms. The first is that if you flow a Lagrangian L by a Hamiltonian vector field, then the result is Lagrangian cobordant to the original L. It's an explicit construction. And the second is due to Polterovich. It says that if you take 2 Lagrangians intersecting and resolve the intersection in a Lagrangian way, so that the area bounded between the resolution and the original Lagrangians, the 2 little bits of area you can see in the picture here, both have the same area A, then L1 plus L2 is Lagrangian cobordant to this resolution, this Lagrangian surgery. That's another explicit construction that you can carry out. And then it's a pleasant exercise using these 2 basic constructions to prove this result, that you can actually explicitly compute this Lagrangian cobordism group of the 2 torus. All right. Now, I actually have another answer to the question of what is the mirror to the Abel-Jacobi map, which is more interesting, but more complicated. And this one says, if you take a Lagrangian, which is null homologous, or you can also take a combination of Lagrangians whose sum is null homologous, then you can take the cone on the inclusion from a rank 1 vector space into the singular chains on X that sends the the generator of this rank 1 vector space to the fundamental cycle of L. So if you take the cohomology of this cone, it naturally fits into a long exact sequence, which splits into short exact sequences because the Lagrangian is null homologous. So it gives you an extension of the homology of X by this rank 1 vector space. And of course, extensions of vector spaces are not interesting. The reason this is interesting is that we can endow this complex with a more interesting structure using the open Gromov-Witten invariants, which count holomorphic disks with boundary on L. So in fact, these endow this extension, this cone complex, with a connection which turns it into an extension of variations of Hodge structures over a certain parameter space M, which parameterizes, which plays into the definition of these open Gromov-Witten invariants. So this extension of variations of Hodge structures is mirrored to the Abel-Jacobi map applied to the Chern character of the complex of coherent sheaves, which is mirror to L. So that Abel-Jacobi map lies in an intermediate Jacobian, which can be interpreted as an extension class of variations of Hodge structures. Like maps to an intermediate Jacobian fibration, and this can be interpreted as corresponding to an extension class of variations of Hodge structures. So this these open Gromov-Witten invariants play into the definition of this symplectic version of the Abel-Jacobi map. This is explained in a paper of Morrison and Walker. And Walker used this idea to predict the real curve counts on a certain real quintic threefold, since those are by the reflection principle, those are open Gromov-Witten invariants of the real locus, which is a Lagrangian submanifold. So this, this gave this prediction for real curve counts analogous to Candela, Stella, Osso, Green, and Parks's predictions of closed curve counts on the quintic threefold. And the key player in the Hodge theoretic derivation of those predictions is this symplectic mirror to the Abel-Jacobi map. And these mirror symmetry predictions for these real curve counts were proven by Punter-Apande, Solomon, and Walker using Atiyah bot localization exactly as described in Punter-Apande's talk. Okay, so that's another answer to what is the mirror to the Abel-Jacobi map, and honestly, I don't actually know precisely how to connect the two answers. Okay, so now we've talked about Abel-Jacobi maps and elliptic curves. The next example was that of K3 surfaces. So recall that the Chow group of a K3 surface split as a direct sum of the Beauville-Voisin subring, which is isomorphic via the cycle class map to the Néron-Severi group, so something discrete, together with the Chow group of homologically trivial zero cycles, which is something continuous and massive by Mumford's result. So the first thing to understand is, what does this Beauville-Voisin subring correspond to symplectically? Well, the conjectural answer is that it corresponds to the subgroup generated by Lagrangian spheres more precisely its saturation. And the main evidence for this conjecture is provided by work of Huybrechts and Voisin, showing that Chern characters of spherical objects in the derived category lie in the Beauville-Voisin. So this conjecture has implications for symplectic topology. For example, it says that if you've got a bunch of Lagrangian spheres, they should be Lagrangian cobordant to 0 if and only if their sum is null homologous. That's quite a strong symplectic statement that we don't know how to prove. As a generalization of this conjecture, the Beauville-Voisin subring is the first step in a filtration defined by O'Grady, which looks like it should be mirrored to the filtration by genus of a representing Lagrangian, roughly speaking. We found some tentative evidence for that interpretation. Of course, so the first step in this filtration corresponded to was what's generated by genus 0 Lagrangian spheres. Okay. So the next thing that the other bit of the Chow group of a K3 surface to understand was this Chow group of homologically trivial 0 cycles, which Mumford's result says is infinite dimensional. So let me tell you our analog, symplectic analog of this result. So first I need to tell you about families of Lagrangians so that we can talk about the dimension of a family of elements of this Lagrangian cobordism group. So it's a well-known result that the deformations of a Lagrangian up to Hamiltonian isotopy are in one-to-one correspondence with a neighborhood of the origin in H1 of L, H1 of the Lagrangian with real coefficients. And the correspondence is defined by flux. It says if you've got some family of Lagrangians L of T, that gets sent to the element of H1 of L, sending gamma, a loop gamma, to the symplectic area swept out by gamma in this family of Lagrangians. So we define families of objects of the Lagrangian cobordism group by taking tuples of Lagrangians and the space of all of their deformations modulo Hamiltonian isotopy. And we have a map from this space of deformations into the Lagrangian cobordism group, taking the corresponding element of the space of deformations to the sum of the corresponding deformed Lagrangians. Okay, so this is sort of a family of elements of the cobordism group that are parameterized by some open subset of a real vector space. So there's a notion of dimension for them. And the result we prove is that if X, being a K3 surface, or more generally any symplectic fourfold, which contains a Lagrangian of genus at least 1, then the Lagrangian cobordism group is infinite dimensional, meaning it can't be covered by a countable union of images of such maps with the dimension of the domain bounded. But so someone might, in case someone feels like it's weird to talk about the hypothesis of having a Lagrangian of genus greater than 1. Of course, there are very tiny Lagrangians, but if you're interested in placing extra restrictions on your Lagrangian cobordism group, like being unobstructed Lagrangians or something like that, then you would it would be natural to it would not be such a it would not be kind. The hypothesis would become non-trivial. Okay. So this is our analog of Mumford's result about the infinite dimensionality of the Chow group of a K3 surface. And I feel like maybe it's getting into details a bit, but it's interesting, the structure of the argument, because it compares, it's very elementary, but it compares very directly with Mumford's argument itself. So it's based on the following lemma. If you've got a symplectic four manifold and tuples of Lagrangians L plus and L minus, then the space of deformations of L minus together with deformations of L plus, which define the same class in the Lagrangian cobordism group, can be parameterized as a countable union of open subsets of affine subspaces, which are Lagrangian, or the intersection form. I should say what this lives on. This is on so since this is a symplectic form, any Lagrangian subspace is at most half-dimensional. And the proof of this is quite elementary. It just says there are, by the simplicial approximation theorem, there are only countably many homotopy classes of cobordisms, and each gives rise to such a family ZV, whose tangent space is the image of the restriction map from cohomology rank 1 degree 1 cohomology of V to degree 1 cohomology of the boundary, which is well known to be a Lagrangian subspace for the intersection formed by Poincaré-Lefschetz duality. A well-known argument there. So it's kind of a relatively elementary argument, but it, and then to complete the proof, you use this bound on the dimension of these spaces ZV and together with the fact that you can't cover a real vector space with a countable collection of positive codimension affine subspaces. So it very close, although it's an elementary argument, it very closely mirrors Mumford's argument for this infinite dimensionality. Okay, and since I'm basically coming to the end of my time, oh, no. I'm going to conclude with the analog of this Bloch-Beilenson result, which said that if you only look at the part of the Chow group of homologically trivial zero cycles of the K3 surface generated by points defined over a number field, that bit is very small in contrast to Mumford's result saying the whole thing is very large. The bit that's defined over a number field, generated by points defined over a number field, is torsion. So if we tensored with Q, it would just be 0. So what could be the symplectic analog of this? Well, it's a natural question to ask how much of the Lagrangian cobordism group is generated by rational Lagrangians, which are Lagrangians also called Bohr-Sommerfeld. So these are Lagrangians where any class they bound has rational symplectic area. So the rational deformations of a rational Lagrangian are parameterized by the rational points in this subset UL, which I defined up above. Rational points in this real subspace. And of course, the proof of this infinite dimensionality result doesn't work at all if you're working over the rational numbers, because of course you can cover a rational vector space with a countable collection of positive codimension affine subspaces. So that's what we expect might be the analog. It's very tentative, but that might be an analog to this kind of question about bits defined over number fields. And I don't have time to talk about the rest, which is in a different direction anyway. So this is a natural point to stop. Thank you very much.
Very much for this nice talk and nicely organized talk. Would you like to display your last slide for us?
Certainly.
Even if you don't have time to talk about it, so those who can get something out of it might find that useful.
Sure.
So are there any questions from the floor, first of all, please?
I'm a little bit puzzled by your focus on Chow knot, the dimension zero cycles. So for example, if you take the valence and block conjecture, if you look at the Chow 1 version of it, so there's the statement that over a number of these are finitely generated, right? Do you have an analog of that statement in the Lagrangian world?
No. I mean, I mean, I was only thinking about that in the context of K3 surfaces,
right? Where
I mean, Chow 1 is just isomorphic to the Picard group, and I don't have, I haven't thought about. I mean, the thing is that this degree filtration on the Chow group, right, is not very natural in the symplectic world. It's only your Lagrangian cobordism group only acquires such a, I mean, it acquires a filtration by degree if you endow your symplectic manifold with extra structure. So it's not very easy to think about such a question. Right. And also, I mean, this statement of a consequence of the block valence and conjectures we took from Huybrecht's book, and I have virtually no understanding of these conjectures beyond that. Just there seemed to be an interesting analogy with this natural symplectic.
No, I agree. It's interesting, but it's just that the valence and block conjecture is really widely conjectural. People have no idea, I think, how to prove these things. So I wondered if in the symplectic world you have something more concrete. But...
yeah, no. I mean, what I just said, this result, this question, how much of the Lagrangian cobordism group is generated by rational Lagrangians? I have the only bit of information I have about this question is that the techniques I was just discussing are useless for attacking it. But I have no hope of getting. I have no more intuition. It just seems in a similar direction.
Ivan, is there any questions?
Nothing in the chat, but yeah.
Ivan, would you like to add something yourself? Any comment?
Not at all. Beautiful talk.
Yes.
You talked about families of Lagrangian submanifolds. I know sometimes in Calabi-Yau threefolds you have Lagrangian torus vibrations. I don't know if this is related to you've got things mapping down to B here. I know you sometimes have mirror pairs have Lagrangian torus vibrations over a common base. And I was wondering if any of this, you could deduce anything about Lagrangian torus vibrations from this program.
Our approach has more been to, I mean, on this final slide, that this picture is precisely of Strominger-Yau-Zaslow dual Lagrangian torus vibrations. And the idea on this final slide is to use that to, well, so the Lagrangian torus fibers in X correspond to points, i.e. 0 cycles on Y. So guiding the Strominger-Yau-Zaslow philosophy guides how we try to translate questions, to translate ideas about 0 cycles into questions about Lagrangian cobordism. For example, both results, which I describe on the right-hand side of this slide, talk about cob superscript fib, meaning the Lagrangian cobordism group of fibers of this Lagrangian torus vibration. So since both of these 7 and 8 were both about 0 cycles, in order to actually prove analogues of these, we had to restrict ourselves to the very specific Lagrangians which we know correspond to 0 cycles. So we sort of, we didn't use these ideas to say something about Lagrangian torus vibrations, but we needed the Strominger-Yau-Zaslow picture of mirror symmetry in order to accurately translate these results about 0 cycles.
Thanks.
I think time's moving on. Let's thank Nick again.
Thank you.
We've got a couple of minutes before the next talk, or 2-3 minutes, if you'd like a short break. Or please be back.
You know, like